Okay, thanks a lot. Yesterday, Shannon Curry in the Formation and Evolution section talked about atmospheric escape from Venus and Mars. This presentation will be in that same ilk or vein ilk, one of those things, but be focused exclusively on Mars. So let's start not with atmospheric escape, but the motivation for thinking about atmospheric escape at Mars. The general consensus is that Mars was once habitable, and there I'm using the definition of that term that was used by Ravi earlier today. It could support stable surface liquid water for long periods of time, but has changed since. And so these are some examples of the geologic evidence, the geochemical evidence. There's also evidence from the atmosphere itself that the atmosphere has changed in big ways. And I also want to stress the fact that the interpretation of each of these things is debated among the Mars community. But there seems to be general consensus that the atmosphere changed in big ways and was at least episodically much more substantial than the 6 or 7 millibars that we observe today. So that leads to a natural question: where did the atmosphere go? There are only two answers to that question: up or down. We think both happened on Mars. If you don't go up or down, then congratulations, you're still in the atmosphere. And so to what extent did atmospheric escape help Mars undergo some sort of climate transition? And there are two reasons to think that atmospheric escape might have been important. First of all, Mars is smaller than Earth, so it takes less energy to escape from the planet and the atmosphere. And also, something that we'll hear about in a couple of presentations, Mars lacks a global magnetic field, and there's a debate in the community right now about whether that matters for retaining an atmosphere. So given this motivation for studying atmospheric escape, I want to talk about some of the escape processes, review the ones that Shannon presented yesterday, but also make the case that Mars is an especially good object for studying atmospheric escape in general at planets. So our star drives atmospheric escape, and that term is a catch-all term that includes many different physical processes. It might be roughly equivalent to saying internal heat drives geology. Escape is lots of different physics, many different PhD theses, many different careers for people who are studying very different things. But in general, they're all driven by interactions with the host star. So a poor, vulnerable planet like little Mars over here that I'm sure you're feeling great sympathy for at the moment, lacks a magnetic field that might be important. It has an atmosphere, and the top parts of that atmosphere are charged through interactions with sunlight and photons, and that creates an ionosphere. And all of these things interact together in different ways. And those interactions can result in providing particles in the atmosphere with sufficient energy to escape from the planet. So here's just a quick review of some of these processes. Ion escape can occur through multiple mechanisms. If you remember back to your E&M class, you might remember this thing called the generalized Ohm's law. This is really an equation for an electric field that a particle can experience, and there are many different terms in that equation. Each one of those terms can accelerate charged particles away from a planet. They can work in concert together, or one of those terms can dominate. So there are roughly 3 different important terms in Ohm's law for removing ions from a planet. And this can be important for Mars for species like O+ and O2+, massive species that are abundant in the upper atmosphere. Let's keep those there in background, and then also mention the process that Shannon said yesterday, sputtering. Some of those ions, as they're attempting to gyrate away from the planet in the stellar wind, crash back into the planet because the planet's in the way. The polar bear jumps into the lake, and that splashes things out. This can be neutral species like O or O2, but also more massive species than that, like argon as well. Photochemistry can remove neutral oxygen, also nitrogen as well, and carbon too, but we think oxygen is probably the most important one at Mars. If you think of a molecular ion, O2+, sunlight can drive dissociation of that ion, and then the resulting atoms have sufficient energy to escape from a small planet like Mars, maybe not enough energy to escape from a larger planet like Venus or Earth. Hydrogen escapes thermally through Jeans escape, or through genes escape, and you might think that I would have put this process first. It's usually the first one you learn about. It's the easiest one to think about, but there's a reason I put it at the end that will come up later. But if you give a hydrogen atom enough energy just because it's part of a thermal distribution, some fraction of that distribution will escape from the planet. This is really only important for hydrogen at Mars, not for oxygen or the heavier species. And so if you add all these back together, then it's a deliciously complicated obstacle. Since this is a formal presentation, that's how I will express that. Something that you could spend an entire career on if you would like. Also, when you start adding extreme events like coronal mass ejections, flares, co-rotating interaction regions, stream interaction regions, those are slightly less intense. And I've forgotten one as well. Solar energetic particles as well. Then there are lots of things to think about. And then on top of that, Mars has small scale regions that are very strongly magnetized. So it can play host to the types of processes that we observe happening in Earth's magnetosphere as well, that can remove particles from Earth. So photochemical escape can't happen at Venus. It's too big. And I'm one of the people that would like to see a Venus mission too, but Mars is a better place to study all of the escape processes. And it has Earth-type escape processes happening too. If you want to study or learn about how escape works, go to Mars. It's, Earth-type escape processes in the auroral zones, and I don't think any other solar system object offers this variety, this richness of physics for these kinds of topics. Another reason to think about studying these processes at Mars is there's a very long baseline for relevant observations. These are some of the missions that make observations relevant for escape: the upper atmosphere, the magnetosphere of Mars, and space weather. There are others that are coming. The Emirates Mars mission will launch in just a few months. The ESCAPADE mission that Shannon mentioned yesterday, the dual spacecraft mission, that's in development now. So not only is there a long baseline going back decades, but there's a long continuous baseline going back almost to the time that the first main sequence exoplanet was reported as well. These dashed lines may be optimistic or pessimistic depending upon your view of how long these missions that are still active will last. I'm going to focus a lot on MAVEN, which is a mission that I'm involved with, currently orbiting Mars, the Mars Atmosphere and Volatile Evolution mission. That's where the N comes from. Okay, the main result from MAVEN, as Shannon presented yesterday, is that we think atmospheric escape mattered at Mars. The physics is wonderful. It's really fun to study, but it could be important, and we think it has been important for the whole planet as well. So rough order of magnitude estimate would be 0.5 bar of atmosphere has been removed over time by this full suite of processes. That's a very coarse estimate with large uncertainties in many different areas. So if you want to say 200 millibars, people won't squeak too much. If you want to say 1.1 or 1.2 bars, people also won't squeak too much with that kind of an estimate. So that's how coarse the estimate is. But compared to the 7 millibars that are there today, it means atmospheric escape is important, and you need to keep it in mind for Mars. So given what we've been learning about these escape processes from Mars, a fun thing to do and an informative thing to do is think about what would happen if we took Mars and plopped it around an M Dwarf. And so saying that I plopped Mars around an M Dwarf and gadonked about it isn't quite tight enough a statement. So I've attempted to tighten it more here. Let's take Mars with 0.5 bar and a CO2 atmosphere. How long would that atmosphere persist if the planet were geologically inactive, so there are no source processes, occupied the habitable zone of an M Dwarf? So that means you have to move it much closer to the star than Mars is today. The campfire is smaller, so to get the same amount of warmth, you have to move closer. But M Dwarfs are very active, so the spitting from the campfire now may become more important because you've moved closer to that fire. That was a lot of analogies in one sentence. I'm sort of ashamed. Okay, so the first thing to check are blow-off conditions. In planetary science, we call that hydrodynamic escape. In the exoplanet world, sometimes you call it hydrodynamic escape, sometimes blow-off, sometimes photoevaporation, which is a term that was actually borrowed from a whole different area of astrophysics having to do with disks, but has now been ported over to planetary atmospheric escape. You can check the escape parameter for a Mars-sized planet orbiting an M Dwarf, and you can do a lot of hand waving. And, ooh, the green did not show up, but that's okay. I can show you where the sort of a heuristic habitable zone would encompass both of these two planets. And if you're saying 100 degrees range in effective temperature defines a habitable zone, then the habitable zone might go something like this. There. And if in your temperature for the escape parameter, you assume the effective temperature for the planet or the equilibrium temperature for the planet, which is the wrong thing to assume, then the blow-off conditions would be here. Mars or Earth would have to move this much closer to the sun in order for hydrodynamic escape to commence. That's the wrong temperature to use. But what this tells us is that in order for blow-off to happen, the exobase temperature, which is the proper temperature to think about, would have to be considerably larger than the effective temperature of the planet. So that suggests that other escape processes may be important. Hydrodynamic escape we can't assume is happening on every Mars-sized planet orbiting an M Dwarf. We have to think of these MAVEN and Mars-type processes as well. So let's march through these processes again, this time showing in several cases a little bit of MAVEN data. Ion loss by all of these processes has been mapped with MAVEN, and we see different channels for ions as they're leaving the planet, usually through some combination of these terms in Ohm's law. And we can see that in an average sense, or we can add up how much escape is happening as the EUV flux from the sun gets brighter or dimmer. And we see that in total, as EUV increases, so does escape. No one is particularly shocked by that. What's interesting is that the escape through some of these channels is sensitive to EUV, and other escape channels not so sensitive to the EUV flux. So if you think about scaling to what would happen at an active M Dwarf, where the EUV flux is maybe a factor of 5 to 10 times more intense, you would imagine that escape could increase, but it may not be a perfectly linear increase. And so if you start taking slopes of these lines and things like that, you say more EUV flux means more ions are produced, more things could escape, and the escape rate might go up by a factor of 3 to 10 or something like that. We're all friends, so we can be loose with those numbers. More ions also impact some of these other processes. I used impact not as a pun, although I just realized that maybe it should have been. So next time I give this talk, I will use it in that way. Sputtering, however, in order to have sputtering, you need these polar bears crashing in. I love the polar bear analogy. I'm going to use that forever now, Shannon. The polar bears crashing in and the stuff splashing out. The ions are the polar bears, and if you produce more, you might expect sputtering to increase as well, maybe a factor of 5 to 10 or 3 to 10, something like that. Photochemical escape, which is so important for oxygen today at Mars, moves up and down and up and down and up and down as a function of time as measured at Mars. But you notice that this expression starts with a molecular ion. If you have more molecular ions, you might expect more escape to happen as well. Thermal escape, which I saved for last, the easy process, is surprisingly complicated, and that's because it's important for a trace gas in the Martian atmosphere, hydrogen, which is not there in abundance. So for hydrogen to escape, you need diffusion to have happened. It's a diffusion-limited process. You need to get hydrogen from down low to up high, and there's this cold trap in the middle of the atmosphere that it's hard to get hydrogen past. Turns out not as hard as we thought as a result of MAVEN observations. There's stuff I can tell you about at another time. But we think that the escape should increase, probably maybe, but photochemistry is hard. The upward diffusion of H should increase, and we think that's over maybe 10 million year timescales, and that's because if you're removing more oxygen by these other processes, the photochemistry will lead to a buildup of H2 in the lower atmosphere, which should lead to increased diffusion through the cold trap and to escape. The spectrum of the star is important as well. If you have enhanced near UV flux, then you might be dissociating water at very high altitudes, and that should lead also to increased hydrogen escape. And then finally, these extreme events should increase escape lots. And that's because M Dwarfs can be very active. The events at M Dwarfs are 10 to 100 times more intense, we think. We need observations. And we think they could be 1,000 times more frequent. And this is the MHD model for that solar storm that Shannon showed yesterday. Sort of a visualization of this same model was shown yesterday by Shannon. Here's Mars over here, here's Venus, and here's a big solar storm going past in 2017. Through MAVEN observations and models, we looked at each of these processes that I've mentioned. And here, just as an example, thermal escape. A thermal escape model fed by MAVEN data showed that the thermal escape of hydrogen increased by a factor of 5 during this relatively moderate storm. We're also learning that these storms are a lot like cats. They do whatever the heck they want. Some storms result in increases in escape of a factor of 1,000 over short periods of time. Others have increases of escape that are maybe 50% or a factor of 2 or something like that. But we think at M Dwarfs, escape should increase significantly because active M Dwarfs are so active compared to our star. So to synthesize and get to caveats, here to sum up is everything that I just said in the last few slides. Ion loss should go up. Photochemical escape should go up. Sputtering, we think, should go up. Thermal escape should go up without a number there because photochemistry is hard. And then extreme events should make escape go way, 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 way up. Sad day for Mars. And we think the atmospheric retention time scale, if the atmospheric retention time scale on Mars today is on the order of 1 billion years, 1,000 times less means 1 million years or less for atmospheric retention for Mars in a habitable zone around an active M Dwarf. You should be wary about everything I just said, because I am too. There's a lot to be done. I glossed through a lot, and I made some energy-limited assumptions along the way that may not be true for Mars. And extrapolation is particularly dangerous. Extrapolating data beyond where the range of parameters that you've observed, extrapolating models is absolutely necessary and always fraught with peril. Sputtering, that process I talked so confidently about, we have no observational evidence yet that it actually occurs at Mars. The dependence of loss on drivers that I showed for EUV flux, that had 2 points on it at low EUV and high EUV. Now that we've had more time with the MAVEN observations, there's suggestion that this trend with escape in EUV flux turns over and may be limited or asymptote at some point as you move from energy limited to more of a supply limited situation. The photochemistry is very sensitive to the input spectrum. Depending upon the features in the NUV, you may produce so much oxygen, so much ozone in the lower atmosphere that the hydrogen diffusion can be inhibited as well. These are all things that more sophisticated models than what the back of the envelope work that I presented here need to address in the coming months and years. There's a lot to be done as well. We're not just saying this is hard and walking away and crying. We should address these issues on the previous slide, and we can. We should continue making observations at this cool obstacle with lots of physics over a full solar cycle, and maybe even a more robust one than we've been having. I talked about MAVEN. I know several of us in this room, maybe multiple different groups, are thinking about MAVEN. Or EVEN. As a matter of fact, an EVEN type mission is currently under consideration in heliophysics at the mid-X level. It's called MEMEX. It has 2 spacecraft orbiting in polar orbits, slightly offset so that they're on top of each other in the auroral zones where escape occurs. We need to merge the magnetized and unmagnetized communities because they've been thinking about these processes and branched over the past 20 years or 30 years or so, and start pulling in giant planets as well. There's a lot to do on the exoplanet side also, and then we need to make these two sides of progress talk to each other. So I'm going to stop with this slide. I'm going to say atmospheric escape has been important for the planet at Mars. It's not just fun physics, it actually matters. Putting Mars around an active M Dwarf seems kind of cruel because it reduces the retention time for that atmosphere. But if you put Venus or Earth around an M Dwarf, the story might change quite a bit. And then I think maybe the most important thing for you to take away from what I just said are all of these caveats. It's a complicated system, lots of complicated physics, and there's a lot of modeling and understanding that's left to be done. All right, thanks a lot.